Okay, so we had agreed that phi of x acting on the vacuum, this is equal to a one particle state. One particle state. So when we act with phi of y on phi of x, well, what could phi of y do? There's two things it could do. It could create a particle because it has a creation operator in it. So this would be with the alpha p dagger, or it could destroy because it's got a destruction operator in it. Okay, so if it creates, what will we get? We'll get a two particle state. And if it destroys, we'll get a naught particle state. Now, I want to remind you of something. If you take the naught particle state against the two particle state, well, remember what this looks like. The naught particle state is just the vacuum. The two particle state, there might be some integrals and some coefficients and everything else, but you're going to get an alpha dagger of one momentum and an alpha dagger with a second momentum. And we know that alpha dagger annihilates bra vacuum. So these operators will annihilate bra vacuum and you'll just get zero. So the naught particle state is orthogonal to the two particle state. So if I was to calculate this quantity, let me take the overlap of naught, phi of y, phi of x, naught. Well, this piece of the state, so that state over there is a two particle plus a no particle piece. But when we overlap with the vacuum, we only catch the no particle piece. So only the no particle piece will appear in this amplitude. And what is this equal to? This is the amplitude that a particle created at x mu, so this is some time in some position, is destroyed at y mu. Destroyed or detected, okay? So this is one thing that our field can do. We can use it to work out the probability amplitude. So let's just draw a little space-time diagram. There's t, there's x. So we create a particle at the space-time event x mu, and we're now learning what's the probability to detect it at space-time event y mu. That's one thing we can do with our field. In fact, there's a very interesting class of questions that we can now motivate. So let's take the vacuum state, naught, and let's use our particle, our field, sorry. Let's act on it with phi x1, phi x2, phi x3. And let's imagine that these fields act in the very distant past, okay? So there is t. This is x1, this is x2, this is x3. So this is like we're creating particles. And then in the very distant future, let's try to detect some particles, okay? So in the very distant future, let's call this y1 and y2. So you should imagine the bottom of the graph is very, very far in the past. The top of the graph is very, very far in the future. And then what these particles will do, we'll shoot them at each other, okay? So we'll shoot them at each other. Something will happen. We want the probability that they are detected at some point in the future, and then we calculate the overlap again with the vacuum naught. So using our field, we can create a whole bunch of particles in the past. They will interact, And then we can see what we detect in the future. Now, if you think about collider experiments, scattering experiments, what do? Well, we have some initial particles. We throw them at each other, say in the LHC at CERN. We shoot these two beams of particles at each other, and we want to calculate the probability of what we catch after the particles have scattered, so a long time after the experiment has happened. This quantity that I have defined here of my field, this would be called a correlation function. And by studying correlation functions, we can, in fact, understand scattering experiments. So I hope that now you've got a bit of a feeling for our quantum field. Our quantum field, the Bayesian equation, the Klein-Gordon equation, you know exactly what the form of the quantum field is. There's a mode expansion for our quantum field. There it is given over there. We know how the creation and annihilation operators are defined. You've got some physical intuition about this quantum field, the axioms that we specified to say what it is. You know what's being quantized. It's the amplitudes of modes of this field. And finally, because phi can create and destroy particles, we can naturally use it to describe the kinds of situations that you find in scattering experiments. This last explanation of relating correlation functions to what happens in scattering experiments was very incomplete, and we're going to have to come back and make this more precise and finish it off. There's a lot of theory that's needed here, but I hope that you've got the general idea. So this was the introduction to the scalar field. That was the end of the ideas that I wanted to introduce in this chapter. We're just going to have a little bit of discussion about the problems that you need to solve.